One of the reasons that we use all of these different kinds of trees and lists and whatnot is to deal with data in a very efficient manner. I want to talk briefly about different ways that you can create lists and talk about something called efficiency that deals with this. For example, you could create a list in a couple different ways if you had them in order. So you could do an array where you just have the numbers in order, or you could have a linked list. In both of these particular situations, what you're dealing with is you have your numbers here, and in order to find a particular number, you just walk through the list. In this case, what we're doing is we're using this special notation called big O notation. The total number of things in the list we're going to call n. So if you have 50 things, n would be 50. If you had a billion things, n would be a billion. And the idea with this is, in the worst case, so the number I'm looking for is at the very end of the list when I walk through the whole thing. That's what this little formula is referring to. In the worst case, I would have to walk through the entire list, so through all the things in my list and find the very last one. In that case, that's how long it's going to take me to retrieve something out of my list. Linked lists is a similar situation for this. So you walk through. Now, arrays are slightly different in that if I know where a particular value is, so I know it's in the 17th slot, the computer actually just does the addition, finds the 17th slot, and goes directly to it. So in that case, what we do is we call it a big O value of 1, in that I do one operation and I basically find the value I'm looking for. Now, even if I knew that the 31 was in a particular spot in my linked list, I don't have a pointer to it. I still need to walk through the list. So even so, retrieval for a linked list is still big O n. So what about inserting things in? So if I want to take this 11 and put it in, with an array, what I would have to do in order to keep it in order is move everything down and put it in here. So in that case, once again, each operation, you might consider it one step, whatever that is also big O of n, because I would have to move everything in the data structure down in order to actually place it in. Now, one other thing I should mention real quick is that when we're looking at these efficiencies, if this was a record or some other large class instead of just a number, each of these operations might take longer, but we're making the assumption that all of the operations take the same amount of time, whatever that time is. So if it takes 50 microseconds for a swap, we're assuming that it would be 50 throughout. And we're just looking at, in general, what the number of steps would be, whatever that time step is. Now with an array, when you delete things, you have the same issue where you delete it, you'd have to move everything back up. So once again, you would have, in the worst case, big O of n. Now in linked lists, when you have something and you need to place it somewhere in the list, if you know where you need to place it, so the 11 we knew we had to place here, if I know where I need to place this 11, so I've already done my retrieval, the only thing I'm changing is two links, here, and we're done. So insertion is order of 1. It takes basically one operation to do that. And deletion is the same idea. I've changed two links, big O of 1 again. So now let's look at a binary tree. So this is the one where each node might have two children. The reason why binary trees are a little more efficient is when we're doing retrieval, in the worst case, we're actually walking down the tree however tall it is. So the height of the tree here, it's in this case 2, is how long that retrieval is going to take. So this is if in a binary tree, the height of the tree is a logarithm. In particular, it's log base 2. We also just say LG as a shortcut for log base 2. So if you see LG, that's exactly that. So that's actually how long, in the worst case, it would take to get to the size of the tree. Now that's assuming a perfectly balanced tree, by the way, though. If it was all down one side, we're no better than a linked list. Insertion is the same sort of thing. So if it's perfectly balanced, logarithm. However, if it's unbalanced and it's all down one list, you have the same sort of problem you have in a linked list as far as retrieval and insertion. Deleting is the same sort of thing. So unbalanced trees are basically exactly the same idea as a linked list. In this case, what I've done is I've included retrieval in insertion and deletion, so we don't need to multiply those together. Let me show you in general like what a logarithmic looks like. So why would logarithms be better than just a regular thing? So let's say that our n is 1,000,000. So an order n operation would take 1,000,000 steps, whereas a log base 2 would take about 20 in a perfectly balanced tree. So 1,000,000 steps, 20 steps. This is why the efficiency of the algorithm actually matters. It's especially true of large data sets. So if the height of the tree matters, it would make sense that all you need to do is just make the tree have more children, and then the height of the tree would be shorter, right? And that's exactly the idea behind a 2-3 tree. So with this, instead of having 2 children, a node has potentially 3. So nodes can have 2 values inside of it, and then the children are basically either smaller than the left number, larger than the right number, or between the 2 numbers. And then the same sort of thing happens with these at different levels. So this is an example of a 2-3 tree. Now, what about if you want to insert something into a 2-3 tree? So let's say we want to put the 7 in. If you just walk down to the furthest down leaf you have, if it doesn't have 2 values already, you just add it into that particular node so that you do have 2 values. Now let's say you want to put this one in. This would be greater than the 10, so it goes down to the right. So what you do is you actually put it in and temporarily have 3 values. And then what you do is you take this middle value, whatever it is, and push it up a level. And split the 2 nodes that were remaining. And this is a recursive call, so that might create 3 nodes in this one, which would then split and go up. So now if we add in the 6, that goes there, it gets split, and the 6 gets pushed up. That's the middle value. We're not allowed to have 4 children, so what happens here is the 10 gets pushed up, and each side becomes its own separate branch. And that increases the height of the tree by 1. All right, so now let's take a look at 2, 3, 4 trees. The idea with this is that you might have as many as 4 children in a particular node. When you're actually doing insertion, there's a lot of things that might happen. I would recommend that you go look at the Wikipedia page on this particular one to learn how it actually works. There's a series of steps for actually inserting things. The general idea is that you split nodes and kind of push the values down the tree in this particular version. But an example. So if we want to insert this 30 into this 2, 3, 4 tree, we start up at the root. If it's a 3 node, we do stuff, otherwise we keep going down the tree. Or a 4 node is technically what it is, which is one of these 3 number ones, which would have 4 potential children. So we go to here, because it's on the left of the 40. It's actually the middle child of this one here, although it appears to be on the right in this diagram. And so we get to this node. Now, this is a 4 node, which is 4 children of a node. And so the way we deal with this is we actually take the 22, the middle value, and move it up and split it into 2 nodes. And then the 22 goes up into its parent. Then we actually descend back down again using the original 30 and start looking for where this goes. So this is in the interval between the 22 and the 36. This doesn't have enough values yet. It doesn't have all 4, so we actually insert the 30 in there. It turns out that the 2, 3, 4 tree is isomorphic, meaning like you could create one out of the other, to a red-black tree. So that's the reason why this one's an interesting one. Generally, it's kind of splits nodes and then pushes down the insertion further down the tree, which is subtly different from what we were doing with the 2, 3 tree.